Number 2. It is weigh-in time for the local under 85-kg rugby team. The bathroom scale used to assess eligibility can be described by Hooke's law and is depressed 0.75 centimeters by its maximum load of 120 kilograms. What is the spring's effective spring constant? All right. So basically, so here we have, right, two states. There's going to be the unstrained, we'll say, scale here. That's the initial. Then somebody jumps on the scale, and obviously the spring is then compressed, right? We're going to take the initial point to be the higher value here, and then the lower part here will be the final point, all right? So technically the change in x here should be negative, and I'll just write that in. So what I now know is that when there is a mass that's placed on the spring, we'll say this guy's mass is 120 kilograms, 120 kilograms. The spring is depressed by 0.75 centimeters, as it's shown here. So the question is now, what is the effective spring constant? Well, the first thing is we would want to draw, I mean, this is fairly straightforward, but to understand the concept, you definitely want to draw a free body diagram of the final point here, okay? So essentially, if I draw a free body diagram that's going to describe this picture, I know that the person has weight, right, which is going to be pointing down. Okay, this is the weight of the person, W sub P. And the spring then will be applying some upward force, right, on that person. Okay, how did I know that? Well, I'll call this F sub S. Well, because, you know, when you step on a scale, you're not accelerating anymore, right? I mean, you step on the scale becomes depressed a little bit here because there's a spring, and then eventually you reach some type of static equilibrium. So that means that your weight has to be balanced by something, right? There is no acceleration. So we know that these two then have to be equal to one another. All right. Without going through all the mathematics, just hopefully that is cool. So the force of the spring will equal then the weight of the person. Now this is an important equivalence because it's going to allow me to do a substitution in my Hooke's law formula. Hooke's law is right here at the upper right-hand side. F is equal to negative kx. That's Hooke's law. So basically now what I'm going to do is I'm going to use that formula. F is equal to negative kx, and I'm going to plug in a delta x instead. So if I were to read this formula out, I don't want you to necessarily read it as F is equal to negative kx, although that's what it says. I want you to have richer detail to that. The force that the spring produces on an object, F, is equal to the negative of the spring constant of the spring multiplied then by the change in displacement of that spring from initial state or resting state to some final or strained state, okay? So expanding on this formula then, I'm going to get F is equal to negative K then multiplied by the final displacement minus the initial displacement, right? And I don't even need to actually expand on this for this problem because I already gave you the change in X and it's negative. So actually, let me just leave that alone. I'm actually going to skip that particular step now. So there's really nothing to do there. The only thing is that I'm going to now substitute in the force that the spring is exerting on the object, right? That's F sub S. That's the same thing as the weight, right? That's placed on the spring. It's the weight of the person, basically, in the problem. So what that means is I can now substitute simply weight of the person, okay, will be equal to negative K delta X. Now, when you plug in the weight here, do not plug in the negative. Why? Because I already took it into account. You might say, well, I don't see a negative. Where did it go? Remember that the sum of the forces here in the y direction have to equal 0 because there is no acceleration. And the force of the spring is a positive value. And if the weight of the person is negative, and I plug that in like this in my formula, right, I plug the negative sign in there. When I do the math, it works out to this. F sub S is equal to WP. I already took the negative into account, you see? All right? So, anyway, getting back to it, it wants to know the spring's effective spring constant here. So, expanding on the weight of the person, you know that weight is equal to mass of the person times then gravity. That's equal to negative K times the change in displacement. I want to solve for K, so just simply divide this by delta X from both sides, right? We're cool with that. And the negative sign goes along with it. So therefore, we have a value now of K is equal to the negative of the mass of the person times gravity, all divided by the change in displacement. So it's going to be negative mass of the person they told us was 120 kilograms, gravity is 9.8, and lo and behold, the change in displacement is negative as I discussed before, but that's in centimeters. You know you need it in meters, so simply divide that by 100. So that's going to be 0.0075, all right, meters. And now just simply calculate, and notice the negatives will cancel, which makes sense. K has to be positive. So negative. Actually, I'm just going to leave the negative sign out because I know they're going to cancel. So 120 times 9.8 divided by 0.0075. And what do we get? So we get a value of about 1.57. 1.57 times 10 to the 345. All right, and that's newtons per meter. Those are the units of the spring constant. All right. It should make sense because it's, as my formula says over here, it's basically weight divided by then displacement. So weight is Newton, displacement is meter. So that's the spring constant. Letter B. A player stands on the scales, and depresses it by 0.48 centimeters. Is he eligible to play on this under 5 kilogram team? So basically, in order to find out is he eligible, why don't we reframe the question, okay? It'll make it easier. Reframe this question. Is he eligible to play on the under 5 kilogram team? Well, it depends on what his weight is. If his weight, or excuse me, his mass. If his mass is under 85, he can, and if it's not, he can't. So basically, let's find the mass, okay? That's the question. What is his mass if the spring is depressed by 0.48 centimeters? So for letter B, I'm going to use the same formula that I talked about here, okay? That the weight of the person will be equal to negative kx, or delta x. So again, expanding on the weight of the person is going to be the mass of the person times gravity will equal the negative k times the change in displacement. I want to solve for the mass of the person. That's the significance of changing the question up a little bit. It helps identify what I need to solve for. And I'm just going to simply divide out the g from both sides, and voila, now I have my formula. So this is going to be negative k, which is the spring constant, right? It doesn't matter if you put 1 kilogram, 5 kilogram, 10 kilogram. The spring constant is constant. Okay, so this is going to be 1.57 times 10 to the 5th, and that's then multiplied now by the change in displacement. They told us it's depressed by 0.48 centimeters. Again, that's going to be negative because we're assuming it starts at a higher point and then it becomes depressed, so the final point is lower than the initial point, and therefore it's traveling in the downward direction if you want to think of it that way. And sure, so here we're going to do 0.0048. That's in terms of meters, remember? Have to convert that, then divided by gravity of 9.8. Let's see what the mass is, and then maybe we can make the conclusion. So it's going to be now negative 1.57 times 10 to the 5th, multiplied then by, I didn't even really need the negatives, 0.0048 because they're going to cancel, divided them by 9.8. And the mass is about 76.9 kilograms. So if that's the mass, according to the scale, can he play on the under 85 kilogram team? Why, absolutely. Sure he can. All right? Or she can. All right? So guys, thanks for tuning in. Appreciate it very much. Please remember to subscribe. Give us a hand. We appreciate it. And we look forward to helping you with more problems. Take care.